Have you ever just looked at a river and thought, what if everything, you, me, the stars, the entire cosmos, was all just a part of some gigantic, invisible flow? Well, today we're going to explore a model of physics that takes that idea very seriously. Okay, let's dive right in.
It's a question that sounds so simple, but the implications are absolutely mind-bending. What if the empty vacuum of space isn't empty at all? What if it's actually a substance? A very, very strange kind of liquid.
So this is the big idea we're unpacking today. In this model, space-time isn't just the passive backdrop for the drama of physics, it is the drama. Everything we see and experience, from the tiniest particle to the biggest galaxy cluster, is just a feature, a little pattern in the flow of this one cosmic superfluid.
Okay, so to even wrap our heads around this, we have to start with the fluid itself. What is this stuff made of, and how do physicists even begin to describe it?
It all starts with something called a complex order parameter. Now, don't let the name scare you. It basically boils down to just two properties. Its density, that's rho, and something called its phase, or theta. A good way to think about the phase is like imagining a tiny clock at every single point in space, and the phase is just the position of the hands on that clock.
And right here we get our first amazing insight. The velocity of the fluid, its flow, is just how fast the hands of that clock are spinning as you move from one point to the next. What's incredible is that this isn't some new made-up math. It's the exact same framework scientists use to describe real-world quantum fluids, like superfluids, that can flow without any friction. We're on familiar ground here, we're just applying it to space-time itself.
All right, but hold on. If everything is just one big seamless fluid, that brings up a massive question, right? How do you get stable, solid things like particles? How does matter even exist?
The answer, believe it or not, comes from something called topology. Because the phase of this fluid has to be consistent. When you get a little whirlpool or a vortex, its circulation can't just be any random value. It has to come in whole number units. Just like the caption says, you cannot have half a vortex. And that means these defects are discrete, and crucially, they are stable. They can't just unwind themselves.
And there it is. That's the huge, radical claim at the very heart of this whole idea. The fundamental particles that make up our world, they aren't little balls of something. They are stable, self-perpetuating whirlpools, topological knots in the fabric of space-time itself. The very building blocks of reality are just persistent patterns in the flow.
So this table here just lays it out super clearly. That stable vortex defect is the particle. And the energy that's all locked up in maintaining that vortex, the energy it takes to keep that little bit of space-time spinning, well, that's what we perceive as the particle's mass, all thanks to Einstein's famous E equals mc squared.
Okay, so we've got particles and we've got mass. But what about another one of those fundamental properties? Electric charge. Well, it turns out the fluid has an answer for that too. And this is the crucial part. We don't need a new rule to explain why charge comes in these neat little packets. It's the exact same topological rule that created stable particles in the first place. The geometry of the space-time fluid itself demands whole number vortices, and it also demands whole number units of charge. It's all part of the same package.
Let's make this a little more real. We can actually build a direct analogy between fluid dynamics and electromagnetism. You can see how the velocity of the fluid lines up with acceleration, or an electric field. The vortex itself, that little whirlpool, acts just like a source or a sink for that field, which is exactly what an electric charge does.
And this is where the analogy gets wildly powerful. Just look at the math. The equation for circulation in a fluid is almost identical to Gauss's law, one of the cornerstones of electromagnetism. It suggests that the laws of electricity and magnetism might not be fundamental at all, but just emerge from the deeper fluid dynamics of spacetime. Charge isn't something on a particle, it's a description of the flow around it. So, this gives us the official definition in this model. It's saying that spacetime itself acts like a dielectric material. A dielectric is just an insulator that gets polarized by an electric field. Here, spacetime itself can be polarized by acceleration. When the flow gets stressed, spacetime has a physical response, and that response is charge density.
All right, this is all great. This fluid model seems to explain what particles are, what mass is, even what charge is. But can it get into the really, really weird details? Like, why do fundamental particles come in 3 generations, each heavier than the last with these super specific mass ratios?
Well, let me introduce you to the Koide relation. This is a real-world, deeply strange formula that has baffled physicists for decades. It perfectly connects the masses of the 3 charged leptons, the electron, the much heavier muon, and the even heavier tau. No one knows why it works. It's just treated as this bizarre coincidence, or maybe it isn't.
And here is the big aha moment. According to the fluid model, this isn't a mystery at all. That magic number from the formula, 2/3, might just be the most stable geometric arrangement for 3 flow modes, 3 vortices to settle into. It's not some deep cosmic number. It's an emergent property of the geometry. Kind of like how honeycombs are hexagonal because that's the most efficient way to pack circles together.
So, we've started small, we've built up particles and their properties right from the fluid itself. Now, let's zoom all the way out and see what happens when we apply these same ideas to the entire universe. When you look at the cosmic scale, this model suggests a universe that's in this constant state of balance between 2 opposing flows. Near massive objects like black holes, gravity acts like a compression force, pulling the fluid in. But way out in the deep, empty voids of space, the decay of neutrons is thought to create an expansion, pushing the fluid outward.
Put those two things together and what do you get? You get this huge, vast cosmic cycle. The universe is constantly inhaling the space-time fluid into black holes, compressing it, and then exhaling it back out, reinflating itself in the voids. It's a universe that breathes.
And this whole idea of a cosmic bounce, it's not just some sci-fi fantasy. This quote reminds us that real physicists like Hal Haggard and Carlo Rovelli are seriously working on models of black to white hole tunneling. They're exploring the possibility that matter doesn't just get destroyed, but bounces back out. It's a very real area of research.
So let's just step back and put this entire picture together. This table shows the beautiful, unifying power of this whole idea. Electric charge is just phase winding. Particle mass is just vortex energy. Gravity, that's just flow convergence. Antimatter is a vortex spinning the other way. Even particle decay is just a vortex splitting apart. All these deep concepts in physics reimagined as simple geometric features of a single flowing fluid.
And really, that's the ultimate takeaway here. In a fluid universe, nothing is truly separate. Particles aren't distinct little things moving through space, they are features of space. We are all just complex patterns in one single flowing cosmic ocean.
I mean, that's a really profound shift in how we see everything. And it just leaves us with this one last tantalizing question. If reality really is a fluid, and everything we see is just the pattern on the surface, what other deeper currents might be flowing just out of our sight? What else are we missing?